Welcome to this video. My name is Mark Scythian. The date today is February 9th, 2025. So this presentation is going to focus on electric vehicle charging versus gasoline vehicle automobile cost analysis. So we have to look at the average power consumption of an electric vehicle per charge. There's about 30,000 watts propelling the car for 1 hour at 70 miles per hour. So this becomes 30 kilowatt hours per 70 miles on average. And then we look at the average cost per kilowatt hour AC electrical power, and that is in the US it's about 17 cents per kilowatt hour. And note that the electrical power, most of it is harnessed from the combustion of hydrocarbon fuels and or natural gas, either through heating water up into steam turbines using natural gas, or the gas turbine power plants driving industrial grade AC electrical generators. So that would be the land non-aeroderivative gas turbine power plants. So one way or another, at least 90% of all of your electrical power is from the combustion of hydrocarbon fuels, either diesel, kerosene, or natural gas. And there just isn't the energy density in solar and wind at the cost effective range. So you're having this pitiful energy density levels of solar and wind. So when people refer to like government subsidized solar and wind, that means all taxpayers in the US are paying for it. So there's really nothing free, and so you have to make that consideration. So the electrical power, 9 units of 10 are harnessed by the combustion of crude oil, and you look at the energy density difference, it's pitiful 10 to 12 joules per pound, or we'll say something in the range of 30 BTUs per pound versus 20,000 BTUs per pound with all crude oil. So you're going to have a cost-effective electrical power based on the combustion of fuel. Okay, so that's where most people, 90% plus, are going to get their AC electrical power to charge their EV. So the next question is, like, what does it actually cost to charge the EV compared to charging a gasoline automobile with filling the gasoline up, that charge, right? So we just take the 30 kilowatt hours times 17 cents, $5.10 USD divided by 70 miles. So that's about 7 cents per mile. But we'll just use the $5.10 price to charge the electrical vehicle to drive 70 miles, let's say on average. I know there's higher end and better EVs that go much farther, but it's about an average of 70 if you take all EV owners. And so then we compare this to the average mile per gallon gasoline fuel economy for the average non-truck like sedan or four-door, etc. And it's about 22 miles per gallon. So if we divide these out, it'll actually cost 2.03 times more, or it is 2.03 times less expensive to charge the EV, but only with a range of about 70 miles on average. I know there's those with like the Chevy Bolt with the advanced features or the latest models, but we're talking about all EV owners on average. So okay, so the EV cost to purchase, we'll just say the EV purchasing cost is 2.5 times more expensive than a gasoline automobile on average. So if you're paying $35,000 for, let's say, a brand new car in the efficiency range, and then you're about 65, 68 after taxes and everything, right? So sales tax, and so that's the average value. So that can be accessed just by looking it up. And so overall cost across the EV and the gasoline automobile is overall an equal value, because you could have a plus or minus 0.5 value, but we'll just say with all the stop and go, the prices are a little higher, a little lower, so we'll say it's about equal. It's about 2.5. It's within that statistical curve. Overall cost between both is equal, and then the environmental impact is equal as well, because the manufacturing emissions, the emissions accrued during the manufacturing process of isotoped carbon and their polymerization, the microwave shielding and inductive shielding structures, the exotic plasticization that goes on, and even with conveyor hood emissions extraction inside of factories, you're going to have various isotopes leaking out into the environment, and not impactful on the environment, but if we were to compare the impact to the CO2 and water emissions, so CO2 is a plant food, so we put more CO2 out, we have more green, we have more forestation, and then water vapor is actually the largest greenhouse gas because it has the highest capacity to store and release heat. The enthalpy metric of 1,000 BTUs of heat to vaporize 1 pound of water. And so if there's a pound of water on the sidewalk and it evaporates, it would have taken 1,000 BTUs over some amount of time. So let's say you're in a sunny environment and it took 45 minutes, you could divide that into 0.45 times 3,600 seconds. So the BTUs per second that water is absorbing to then convert it into water vapor. So you haven't destroyed the water, you just turned it into vapor. You can't destroy or create matter anyway. So what is that implying? That means that water has the ability to absorb large amounts of heat and then convert it into a non-ideal gas of water vapor. So it's still water, still H2O, it's just in the vapor state. And then if we remove that heat from the water vapor, we then get condensation, and then it rains back down from water vapor to water. Okay, so CO2 and water vapor is what comes out of a modern automobile due to the modern automobile gasoline engine. So the gasoline engines made before 2008 are just completely obsolete. They have nothing to do with gasoline engines today, because remember, we have variable valve cam timing, we have direct injection directly into the cylinder, we have anti-detonation sensing, we have volumetric efficiencies at 100% without a turbocharger, and then we have compression ratios that are really high, like extreme, close to 11.8 to 1, like almost 12. And so you're burning all the fuel, and then you're sending it through a super reheating catalytic process, not just a catalytic converter, but it's a dielectric substrate that basically behaves like a thermocouple in reverse. So instead of a heating element, we add heat or electricity to get, let's say electricity to get heat. We can add heat to get electricity. So you turn the catalyzer into a thermocouple, and this reheats and reheats and reheats. So whatever carbon monoxide is going through the output of a complete combustion burn, no unburnt fuel, it's gonna reheat until our empirical equation changes across the CHOXYZ from 74 moles of carbon monoxide to 14 moles of carbon dioxide. So all you're going to get is carbon dioxide and water out of the exhaust of a modern automobile engine. So already it's not really an issue with emissions, but there is still the oxides of nitrogen and the oxides of sulfur, and that doesn't include trace elements that may have an impact on reflecting the sun, so the emissions of methane and the rest of the environment. And that's really the consideration. It's really the methane count that becomes reflective of the sun. So what happens, we should be getting some heat, instead it's reflected, and then we have climate change based on global cooling and global warming together. So that's called albedo versus hothouse. And it's not supposed to be like that, but then again, we do have different changes of the solar magnetic cycle that is causing climate change on all the planets. But of course, all this isn't helping either, right? So if you're concerned about the environment, then it is then inequality between the EV and the gasoline engine, the EV versus the gasoline, right? So if we look at the materials involved in making an actual microwave inductive resistant capacitive charge field that allows all the different components to interact without back voltages discharging out of all the different electromagnetic fields in the EV, we need to make relatively exotic polymerized plasticized structures that are with carbon not having its usual 6 electrons, 6 protons, 6 neutrons. It's going to end up being isotope to make that happen. So again, you run into non-radioactive isotopes that do enter the environment, but it's about as dangerous, or I will say trivial, as oxides of nitrogen and oxides of sulfur in low amounts. So if you do the report card on the emissions with modern gasoline automobiles and then EVs, they're about equal. So overall costs about equal. I mean, that includes charging and maintenance and putting gas in the vehicles, whatever. And then the EV manufacturing is much more toxic compared to the manufacturing of gasoline automobiles, because it's all recycled plastic. There's a lot of 3D printing going on. There's a lot of recycled materials, especially with respect to aluminum, because you don't have to actually extract it out of bauxite. I mean, that's already been done for the last 100 years. So it's very environmentally friendly. And then everything's automated today. Even the scraps are vacuum extracted and then melted back down. So you literally could have factories running autonomously with the lights turned off through geospatial reckoning and cloud-based automation systems. And so that's really the most expensive part, is the real estate. So, you know, that would be moved over to China under the U.S. ownership, and then you can crank out these cars. Now, everything else is economics and politics, and, you know, if people want to get active and, you know, do something about the record profits, that's a separate political economic field. But the physics, the engineering, the science behind it is that we have terrible manufacturing emissions for EVs, but compared to the amount of emissions we would get from burning all the fuel through the modern automobile, it would be about equal. So helping the environment either or. It's just that the car can't be older than like 2010. Okay, they're equal. So we have lower manufacturing emissions in the gasoline automobile manufacturing process compared to the EV process. But then, you know, we have the emissions, even the oxides of nitrogen and the oxides of sulfur, NOx and SOx, we have that. So the overall scientific engineering analysis is that the EV and the gasoline across cost, maintenance, environmental is equal. So we might as well say it's a battle between potato versus potato. So thanks for watching this video and have a great day.